Welcome back to the Deep Dive, where we take these little fascinating nuggets of information and we try to figure out what they mean and why they matter.
I like that.
And today we're continuing our deep dive through the OEIS.
Yes.
That's the online encyclopedia of integer sequences.
It's a wonderful resource.
For all of you number theory students out there who are listening, the OEIS is, it's not just a catalog of numbers.
It's more than that.
It really hints at these really proprofound relationships between different mathematical ideas.
I agree with that.
And today we're diving deep into sequence A000175.
Okay.
And this one was flagged for us by one of our listeners.
Right.
And they were very curious about the short note in the OEIS, which is related to zeros of Bessel function.
Okay. That's interesting.
And also we know that this sequence was formerly known as M2000 N0790.
Right.
That's an interesting little historical tidbit.
Yes.
Now, this sequence starts at the first term, and then the list of values actually begin from index 3.
All right.
But that's kind of just a detail about how they're indexing it.
Sure.
But the real mystery here that we want to unpack today is this connection to Bessel functions.
Yeah, that's really the heart of it.
So what I think we should do first is maybe take a little bit of time to kind of define what a Bessel function is.
Sure. So, I mean, Bessel functions...
Is there anybody out there who's ever encountered one?
Right. So Bessel functions, they really came to prominence through the work of Friedrich Bessel in the 19th century. And they are solutions to a specific type of second-order linear differential equation. And that's known as Bessel's equation. And the equation itself looks like this. X squared times d squared y over dx squared plus x times dx squared plus x times guy over dx plus open parenthesis x squared minus alpha squared close parenthesis y equals 0.
Okay.
So
yeah, that looks like a mouthful.
It does look a little complicated, but the key element here is this alpha.
Okay.
The order of the Bessel function, which can actually be any complex number.
Any complex number. Wow, that's
a
lot of possibilities.
Yeah, there are a lot of possibilities, but the ones we encounter the most and the ones that are most important are when alpha is an integer or a half integer.
Okay, so within this vast world of complex numbers, there are certain kinds of orders that stand out.
Absolutely. And the reason these stand out is that they appear naturally when you try to solve certain fundamental equations in physics and engineering.
Oh, interesting. Okay.
Yeah. So, for example, if you're looking at Laplace's equation in cylindrical coordinates.
Okay.
So you're dealing with problems that involve things like pipes.
This shape really matters.
The shape really matters, exactly.
Okay.
Or cylindrical waveguides, you'll encounter Bessel functions of integer order, and these are often called cylinder functions or cylindrical harmonics.
I see. So the name gives us kind of a clue.
It does, yeah. It gives you a clue about where they arise.
About what's going on.
Yeah.
Now, what about these half-integer orders that you mentioned?
Right. So half-integer order Bessel functions, they appear when you're dealing with the Helmholtz equation in spherical coordinates.
Okay, so now we're talking about spheres.
Exactly. We're talking about spheres now, and this equation is really important in fields like acoustics.
Oh, wow.
When you're studying how sound waves propagate spherically.
So when you say spherically, you mean like emanating out from a point?
Exactly, emanating out from points. So anything that radiates, sound, light, you name it.
Okay.
And also it appears in quantum mechanics.
Wow.
Particularly when you're analyzing systems with spherical symmetry.
That makes sense.
Yeah. So the solutions in these cases, they involve these spherical Bessel functions.
So again, we're seeing this connection between the name.
Yes.
And then the kind of physical reality that it's describing.
Absolutely. The name really hints at where it's used.
And it sounds like these Bessel functions aren't just these kind of abstract mathematical things.
No.
It's really, they're used to describe real-world phenomena.
They are. And it's amazing how many different areas they pop up in.
Wow. Like what?
So you see them describing the behavior of electromagnetic waves in waveguides, the way heat flows through cylindrical materials, even in the radial part of the Schrödinger equation when you're studying atoms.
Gotcha.
And, of course, in understanding how sound radiates from sources, so their applicability is really wide-ranging.
It's really amazing that Bessel himself was initially just studying perturbations in planetary motion.
Right.
Which is a very specific problem.
It is a specific problem.
And yet the functions that he developed have this incredible reach.
Well, it really highlights the power of mathematics.
Across so many different scientific disciplines.
Right.
It's really extraordinary.
It is.
Okay, so we've got this sequence, A000175 in the OEIS.
Right.
And all it says is related to zeros of Bessel function.
Yeah, it's a very concise description.
So now that we have a better understanding
Yeah.
of what Bessel functions are, how do we connect them to this particular sequence of integers?
Okay, so this is where things get interesting.
Okay.
The link is provided by something called Rayleigh polynomials.
Okay, now that is not something that's mentioned
Right.
explicitly in the OEIS entry.
Not in the short description, but if you look in the comments section, you'll find that A000175 represents the constant term of the Rayleigh polynomials.
Okay, so we need to understand a little bit more about these Rayleigh polynomials.
We do, yes.
So first of all, what are they?
Right, so Rayleigh polynomials, they're a sequence of polynomials that come up when we look at the power series expansions of spherical Bessel functions.
Okay.
Remember those half-integer order Bessel functions that we talked about that are relevant in spherical coordinates?
Right, so the ones that describe like sound radiating from a point.
Exactly. So when you express these functions as infinite sums, the coefficients within those series are closely tied to these Rayleigh polynomials.
Okay, so it's like we're taking these spherical Bessel functions
Yes.
and we're kind of cracking them open.
That's a good way to put it.
We're looking at the code inside.
Yeah, like they have this mathematical code.
Uh-huh.
And the Rayleigh polynomials are like specific sections or patterns within that code.
I see. Okay, so the sequence that we're interested in is the constant term
Right.
of these polynomials,
Right.
which themselves come from the spherical Bessel functions.
Exactly.
Okay, now, how do the zeros of Bessel functions come into play here?
Okay, so this is the key connection. The roots of these Rayleigh polynomials
Okay.
are related to the squares of the roots of Bessel functions
Okay.
of half-integer order.
Okay.
So if you find the values where a spherical Bessel function equals 0,
Uh-huh.
those values, when you square them,
Right.
are directly connected to the roots of the corresponding Rayleigh polynomial.
So we're not talking about the zeros of Bessel functions directly.
No.
We're talking about the zeros of Bessel functions
Right.
squared.
Exactly.
And then those are connected to the roots of these Rayleigh polynomials.
Exactly.
Okay. And then this sequence, A000175,
Yeah.
gives us information about those Rayleigh polynomials.
Yes, it gives us the constant term.
That's a very specific piece of information.
It is. It is.
It's like a clue.
It's a clue. It's like a little window
It has a little piece of the puzzle.
into this much bigger,
Exactly.
a much bigger thing.
A much bigger picture.
It's like these integers. They're
Yes.
holding the secret
They are.
about the behavior of these continuous functions.
And it's beautiful how it connects different areas of mathematics.
Yeah.
You have an integer sequence, which is very discrete,
Mm-hmm.
connected to the roots of continuous functions that come from differential equations.
Right, which come from physics.
Exactly. And it makes you wonder how many other seemingly different mathematical objects are linked in such ways.
And, it's not just that this is
Yeah.
a recent discovery.
Oh,
The OEIS entry also points to N.J. Sloan's
right.
A Handbook of Integer Sequences from 1973,
Yes.
where this sequence is also listed.
Yeah.
So this is something that's been known for a while. It has, and it underscores this effort within mathematics to catalog and connect these patterns.
Right. And the OEIS is kind of a modern continuation of that effort.
It is, yes.
So let's recap for our listeners what we've learned.
Okay.
We have this sequence, A000175. It's a sequence of integers.
Uh-huh.
And it turns out that these integers
Mhm.
are the constant terms of the Rayleigh polynomials.
Right.
These polynomials are closely tied to the spherical Bessel function.
Yes.
And their roots are related to the squares of the zeros of Bessel functions of half-integer order.
Exactly.
So it's quite a journey from that simple line in the OEIS
It is, yeah.
all the way to
It's a chain of connection.
all these different concepts in math and physics.
Absolutely. And what I find fascinating is how this simple statement in a database can lead us through concepts spanning integer sequences, polynomial theory, special functions, differential equations that have real-world applications.
Yeah, it really highlights the interconnectedness of math.
It does.
So to wrap things up for our listeners today, think about this. How many other sequences in the OEIS might have these kinds of connections
That's a good question.
that we haven't discovered yet?
It really makes you think about the hidden language of numbers.
Yeah, it's
Okay.
really amazing.
It is.
So we encourage you, our listener, to delve further into the world of Rayleigh polynomials and their relationship with the zeros of Bessel functions.
Yeah, see what you can find.
You might discover something amazing. See you next time on The Deep Dive.
That's good.